is universal for both overdamped and underdamped.
Okay, so other questions or comments? Yes, again in the chat.
Okay, the question is, my speed limit time seems to depend on the time of the protocol itself for inhomogeneous temperature. Okay, so your question is depend on the time of the protocol. So I actually cannot understand the meaning of the question. So maybe I can answer question from Mohammed after the presentation. And also there are another question on the chat. Under what condition can you saturate XTR, making the inequality unequality? So the difference between TOR and XTR is the XTR is always, we can always achieve the equality. So here I did not specify the equality condition, but actually it is the same as when I derive the entropic bound from the XTR. So if you choose G function in clever way, and also we have to choose this function lambda, which is in the definition of the currently observer to be something proportional to the probability current, for example, in the Langevin case, then we can always saturate the inequality.
Okay, so other questions or
So
comments?
Mohammed's question is,
Time? Yes.
I have tau on the left bounded by a quantity that okay. So here P, maybe if you are meaning this P tau is the P tau is the final distribution. So it's actually you can choose this to be a specific distribution. So you can make the right hand side. Okay, maybe you are meaning that this entropy production is uh, entropy production is uh, the function of time, but you can see that in my definition of this t tilde, I have 1 over tau, so the dependence of the tau in the denominator of the right-hand side vanishes. Is this clear for you, Mohammed? Okay, thank you.
Hey, so we still have a minute to take another question. So let me ask a question. So
Yeah.
in the short time limit, so what happens in your hierarchy of TURs?
That's very good question because in the first people have the relation for the short time limit actually XTOR just got is the same as TOR because in the short time limit state dependent observer does not play any role.
I see.
Yeah.
I see. Thank you.
Okay, thank you. Okay, one more
Another
question
question.
from the chat.
Yeah.
Are your extra XTR from Kramerau? Yes, exactly. We derive the XTR using the standard Kramerau inequality. Yeah.
So is that fine with everyone? Okay, so let's thank the speaker again.
Okay, thank you.
Okay, so we are going to the next lightning talk by Pedro Harunari. Can you share the slide?
Hello, do you hear me?
Yes.
Okay, good. Yeah, you still hear me now? I just changed my microphone.
Yeah.
Okay, I'm sharing the screen.
Yes.
Okay, is
Yes.
everything
Thank
good?
you. Yes.
Shall I
Okay.
start?
So yeah,
Okay.
please.
Okay. So, hi everyone. My name is Pedro Harunari. I'm a postdoc in the group of Massimiliano Esposito in Luxembourg. I'd like to thank the organizers for giving me the opportunity to present my work here. I like this conference a lot and I follow it every year. So let's go down to business already. So the object of study are continuous time Markov chains governed by a master equation. And this is like a pretty standard technique in stochastic thermodynamics. If you are unfamiliar with this, I would probably suggest you take a look at yesterday's tutorial by Gabriel Landi. And the only two things we are going to assume is that the network is irreducible and that the probability distribution has already reached its stationary value. So they don't change, they don't evolve in time. We define currents in the pretty standard way. So the current from X to Y is given by the transition rate of jumping from X to Y times the probability of being in X minus the other way around. And this machinery of continuous time Markov chains has been successfully used to model many different systems like configurations of molecular motors and the changes between these configurations. And the question we want to tackle in this problem, in this all of the in the three papers that I will talk about, is if you control one current, how do other currents in your system respond to the current you are controlling? So you can think about it. For instance, imagine you have a heat engine and it is described by a continuous time Markov chain. One of the currents is your energy input, and the other current is the work output. So it's a very pertinent question. How much does the work output changes when you change the energy input? So let's pose the question a little bit more precisely. We choose one input current to be Ji. Depending on your system, you can have different input currents. In this case, it's the current between these two states. And when I say we control the input current, I mean we control the rates of this current in both directions. Can be only one of them or both at the same time independently. What is going to happen is that in the equation for your input current, these rates appear here and they will change, but also the probability distribution will change. So these probabilities change according to what you are doing to the input rates. And it's a complicated function, actually. So if you plot the input current in terms of one of the controlled rates, it's a function that there's nothing very special. You need to solve the system to find these probabilities, and it is a complicated function. But what we want to ask here is how does another current, let's say Je, changes when we control Ji? So I want to plot Je in terms of Ji. And when you first approach this problem, you're probably gonna think, oh, okay, it's gonna be a complicated function. We cannot say much about it. I don't know. It's just a function. But if you had paid attention to the title of my talk, maybe you already know the answer of what is gonna come up, and you're probably not gonna be as surprised as we were when we found out the relation between these two. Okay, one very important symmetry that plays a role in these types of problems is Kirchhoff current law, which was introduced in the 19th century for electrical currents. It basically says that all of the currents going into one node here, they have to sum to zero if you are in stationary conditions, because otherwise you would be accumulating or removing charge from this node, or in our case, the probability. And this cannot be because we are in stationary conditions. And as a consequence of Kirchhoff current law, we can take our network, we decompose it into cycles. So we have these currents representing the cycle currents here, 1, 2, 3, and 4, because we have 4 cycles. And Kirchhoff current law tells us that any current in our system can be written as a linear combination of this set of currents. So this set of currents, they form what we call a fundamental set, in the sense that if you remove these currents, then you are left with no cycles. And the coefficients going into this relation, they are purely topological. They are only -1, 0, or 1. And it is important because the things you are controlling, the input rates, do not appear in these coefficients. So this function is going to be true, and for whatever value of the input rates that you plug in, and the currents will change accordingly, but the coefficients will stay always the same. Okay, but this is true when we have a fundamental set of currents. So our input currents are the fundamental set. But what if we want just one current or two input currents? So what we want to do is to write a Kirchhoff current law type of equation with fewer terms. So the question is basically, are there coefficients instead of these gammas, so in our case, these lambdas, that sort of absorb effectively the contribution from the currents from the fundamental set that are not input? So I just want the input currents on the right-hand side, and these coefficients need to make this equation true and also cannot depend on the controlled rates. So this is the type of equation that I want to find. And it turns out that the answer is yes, there is one for the case of one input current. So in this contribution that was published in PRL last year, we have shown that if you take this input current here, then any other current in your system, so in our case, JE, is going to be linear affine in the input current. Affine because there is also this inhomogeneous term, the affine coefficient. And the coefficients do not depend on the rates of the input edge, but the currents, of course, they do depend. And it basically means that if you take one specific pair of your input rates and you plot them, JE in terms of JI, all of these points are going to fall on this line. And although this is very simple mathematically, I think it's a very deep and very surprising result, at least to me. It is a very unexpected result. And this coefficient, the linear coefficient, we call it the susceptibility because it tells you how much JE is susceptible to changes in JI. And some of the reasons why I think this is powerful is it's harnessing the sensitivity between currents. So how much JE is sensitive to JI, and this is true for any other current in your system. It has predictive power because if it's a linear relation, you just need two measurements and then you get both coefficients already. And I really want to stress out that this is exact. So I'm not doing any approximation close to equilibrium assumption or expansion that I truncate. This is really exact and analytical, valid arbitrarily far from equilibrium. It's a fundamental symmetry of the currents. It's also a way of test-proofing your model because you can calculate the coefficients analytically and compare with the empirical measurements and to see if there's something off with your model or not. And just two brief comments. I said that JE is linear affine with the input current, but also any two currents, JE and JE prime, are affine between themselves. This is like very simple from the previous result. And macroscopic currents that are themselves a linear combination of currents, they are also going to be linear affine on the input current. Again, very easy to see why if you just do the calculation. And so let's get the lay of the land. When I have one input current, then the result that we dub mutual linearity tells us that there is this linear relation. If the input currents are the fundamental set, then there's Kirchhoff current law. But what happens in between? And it turns out that if you take more input currents, you can still get a mutual linearity relation. So what we call mutual multilinearity relation. So you take a set of input currents. They are supported by this set of edges. You can have more than one edge. And we control the rates of all of those edges. The only requirement is the removal of this set of edges does not disconnect the network. If this is true, then yes, you still have a linearity relation between any current in your system and all of the input currents, and the coefficients, this coefficient and this coefficient, do not depend on the things you are controlling. So it turns out that from one input current to the fundamental sets, there are types of mutual linearities between any current in your system and the input currents. But beyond the fundamental set, this cannot be true because otherwise the set of edges would disconnect the network. So you cannot go beyond the fundamental set, but here you have mutual linearities. Okay, just really briefly, one example of application is the myosin 5 molecular motor. This is a well-established model for this molecular motor. And just applying our result, we can show that the consumption of ATP is linearly related to the velocity of the motor when you change the concentration of inorganic phosphates. So for various values of inorganic phosphate in the environment, they always fall on this line, the consumption of ATP in terms of the velocity. And I think this is pretty neat. And to summarize, because I'm almost out of time, we uncovered this symmetry, fundamental symmetry for currents that is true for any continuous time Markov chain, provided that you do not disconnect the network and the network is irreducible anywhere in stationary conditions, offering some sort of generalization for the Kirchhoff current law. We also showed that it's valid for unimolecular chemical reaction networks. And if you take currents that still do not relax to stationarity, then it's not going to be true. But if you take the Laplace transform, it's magically true somehow. And this is something that I still don't know how to go about. I would also like to mention this paper by Faidze and collaborators, where they provide an alternative proof by connecting the susceptibility with mean first passage times. I would like to raise to your attention Christoph's talk later today. He's also doing some identities with Timur and Massimiliano that are very interesting, and it's from a different nature. It's another type of symmetry, and I think it's pretty interesting. And I would like to thank my organizers, Sara, Vivian, and Mateo, and I'm happy to take questions. Thank you.
Okay, thank you